All right, so if you're a computer engineering student and you've ever wondered how we actually teach a machine to predict something, like a house price or maybe even an exam score, then you are in exactly the right place. Today, we're going to break down the foundational blueprint for supervised learning. We're talking about the 4 essential pillars that hold up pretty much every regression model you'll ever build.
So here's our game plan. We're going to start with the big picture, the machine learning pipeline. Think of it as our overall blueprint. Then we'll build our system one pillar at a time. We'll start with the data, build a model on top of it, figure out how to measure its mistakes, and then finally teach it how to fix those mistakes. Any big engineering project, it all starts with a blueprint, right? Well, machine learning is absolutely no different. The ML pipeline is that standardized, repeatable process that guides us all the way from just a pile of raw data to a fully functioning predictive system. This slide lays out the whole process perfectly. The best way to think about it is like a factory assembly line. First, you need your raw materials. That's the data set. Then you feed those materials into the model, which is our prediction machine. Next up, you've got to have quality control, right? That's the cost function. It tells us how well our machine is actually doing its job. And finally, you bring in the algorithm, which is like the expert technician who tunes and perfects the machine. Those are our 4 pillars. Okay, let's dive into our first pillar. Just like you can't build a bridge without steel and concrete, you can't build a machine learning model without one thing: data. This is the raw material from which we forge all of our insights. So what is a dataset, formally speaking? Well, we define it as a collection of M examples. Each of those examples is basically a pair. You've got X, which is your input or features. Think of these as the questions we're asking the machine. And then you have Y, the target label, which is the correct answer we want the machine to learn. It's really just a big list of questions and their corresponding answers. Let's make this a little more concrete. Say we want to predict house prices. Our features, our X values, would be things like the size of the house in square meters and the number of rooms. The label, our Y value, is the one thing we're trying to predict, the price. We feed the machine hundreds or thousands of these examples so it can start to see the pattern, the relationship between them. Now, in the real world, we have to format this data so our code can understand it. All of our input features, the size, the number of rooms, for every house, get organized into a big grid or a matrix that we call the feature matrix, or just capital X. And all the correct answers, all the prices, are put into a single list called the target vector, or lowercase y. This X and Y setup is the standard you'll see in pretty much any library, especially scikit-learn. Okay, we've got our raw materials. What's next? Well, now we actually have to build the machine itself. For that, we need a mathematical model, which is really just a hypothesis about how our features relate to the final answer. This is our second pillar. We're going to start with one of the most fundamental machines out there, linear regression. And this equation right here is its blueprint. Now, it might look a little intimidating, but the idea is super simple. We're just predicting our price by taking each feature, multiplying it by some number, and adding them all up. The really important parts here are those theta values. Think of them as the tuning knobs on our prediction machine. The entire goal of what we call training is to find the absolute perfect setting for each one of those knobs. So yeah, the whole point of this is to find the best possible settings for these theta knobs. Theta 0 is what we call the bias. It basically just shifts our whole prediction line up or down. And all the other thetas are the weights. They control exactly how much influence each feature, like size or number of rooms, has on the final prediction. Training is just the fancy word for the process of finding the optimal values for all these knobs. Okay, so we have a model, we have these knobs we can turn, but that brings up a really important question, right? How do we know when we've found the best settings? How do we mathematically define what a good prediction is versus a bad one? And that is exactly where our third pillar comes in, the quality control system. We need a way to score our model's performance, a function that tells us precisely how wrong its predictions are. Let's meet the mean squared error, or MSE. This is our cost function. Now, don't let the formula scare you. Let's just walk through it piece by piece. Inside the parentheses, we take our prediction and subtract the actual answer. That gives us the error for just one example. Then we square it. And this is a really important engineering decision. It makes sure all our errors are positive, but even better, it heavily penalizes really big mistakes. Finally, we just add up all those squared errors and take the average. And what we get is a single number, our cost, that tells us exactly how well our machine is performing. So the goal becomes incredibly simple. Get that cost number as low as possible. A high cost means our predictions are way off. A low cost means we're getting really close.
The best way to picture this is to imagine a big, bowl-shaped valley. When we start out, our random theta values put us somewhere high up on the side of that valley. Our entire job is to find a path to the very, very bottom, where the error is at its absolute minimum.
So the big question is, how do we find our way to the bottom of that error valley? We need a guide, right? An automated technician that can figure out the path for us. This is our fourth and final pillar, the optimization algorithm. The best way to get this, honestly, is with a simple analogy. Just imagine you're standing on the side of a mountain, completely blindfolded, and your only goal is to get to the lowest point. What would you do? Well, you'd probably feel the ground around you with your feet, figure out which direction is the steepest downhill, take one small step in that direction, and then just repeat that process over and over again, until you can't go any lower. That whole blindfolded on a mountain idea, that's exactly what this gradient descent formula is doing, just in math terms. Let's look at this rule. To get a better value for any of our theta knobs, we take its current value and we subtract a little bit. How much? Well, that amount is decided by two things. First is alpha, the learning rate. That's the size of the step you take. And it's a classic engineering trade-off. If it's too big, you might jump right over the bottom of the valley. If it's too small, it could take forever to get there. The second part is that derivative term. That's just calculus for finding the slope of the hill. It tells us which direction is the steepest way down. And here is the best part, especially for us as engineers. We can map all of this theory directly to just a few simple lines of code. Pillar 1, the dataset, that just becomes your X and Y arrays. Pillar 2, the model, that's as simple as writing linear regression parenthesis. And Pillar 4, the entire optimization algorithm, it's all hidden inside one powerful command, .fit. That single method does all the hard work of walking down that error valley for you. And the result of minimizing Pillar 3, the cost function, is what you get at the end. You can just inspect the intercept underscore and coefficient underscore attributes to see the optimal theta settings the model found. I really can't overstate how important this is. This core idea of defining a cost and then taking these small iterative steps downhill to minimize it, that isn't just some neat trick for this one problem. Gradient descent is the fundamental engine that powers nearly all of modern machine learning, from this basic model all the way up to massive neural networks. So there you have it, dataset, model, cost function, and algorithm. This four-pillar structure is an incredibly powerful blueprint for predicting continuous values. But I want to leave you with a final thought to chew on. What if you wanted to do classification instead? Like identifying if an email is spam or not spam. Which of these four pillars do you think you would need to swap out to make that work?